Good evening, ladies and gentlemen, and welcome to the SAIEE Gauteng Centre webinar on the impact of renewables on grid stability. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the CGC, the Central Gauteng Centre playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. You will also find the link to register on the SAIEE TV in the chat box. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now tonight to our host, Bongokuhle Nkwanyana, who is running the governance portfolio for the Central Gauteng Centre. And he's an electrical engineer at the National Transmission Company of South Africa Operations Planning Department. He holds a Bachelor's of Science in Electrical Engineering from the University of KwaZulu-Natal and a Government Certificate of Competency from the Department of Employment and Labour. In the 6 years of his career, he has worked for 4 years in a power station, 1 year in a factory, and is now in the systems operations environment. Over to you, Bong.
Good evening. I hope this finds you all well. Today we are privileged to have Mpedi Rampokanyo as our speaker for today. So Mr. Mpedi Rampokanyo is a professional electrical engineer with 17 years of experience in the power sector, focusing on renewable energy integration and power system operations. He has a Bachelor of Science degree in Electrical Engineering from the University of Cape Town and a Master of Engineering in Electrical Engineering from Wits University. He is currently working as a Managing Director of Rampox Pty Ltd, an engineering, construction and consultancy firm based in South Africa. Welcome, Mr. Mpedi. You can continue.
Thank you, sir. I'm having a bit of challenges sometimes with the network. It's a bit intermittent today. Please excuse me. I just hope that it stays stable for the rest of the webinar. Okay, I will now share my screen. Can you confirm if you can see my screen?
Not yet. We're waiting to view it.
Oh.
There we go.
I'm on it now.
Yeah. Presentation mode, please. There we go. Please proceed.
Okay, great stuff. Thanks a lot. Okay, good evening, colleagues. And as the introductions have been done, my name is Mpedi Rampokanyo, and I will be presenting the impact of renewables on grid stability. So that's the topic for today. I just want to get something out of the way. Just give me a second. And there we go. Okay, thanks a lot. Yes, so as I said, my name is Mpedi Rampokanyo, and I'll be presenting this topical topic. That is the impact of renewables on grid stability. Just to take you through the presentation outline for today, we will first discuss the background on energy transition. Then we'll touch on power system definition. We also will discuss some implications in terms of transient stability considerations, as well as frequency stability considerations. We will also touch on mitigation measures that are in place, obviously, to combat the problems that we have due to this integration of renewable generation, where there are problems. We will further do some takeaways, key takeaways and conclusions, that is looking at future system studies, how those should be done, as well as a few concluding remarks in terms of the other issues that we need to be aware of as we transition. Power system stability, in terms of the classical or traditional classification that we know, is defined as the ability of an electric power system for a given initial operating condition to regain a state of operating equilibrium after being subjected to a physical disturbance, with most of the system variables bounded so that practically the entire system remains intact. So that's the classical definition as given by IEEE and SAIEE. And we know that power system stability is categorized into 3 categories. That is traditionally, that is angle stability, frequency stability, and voltage stability. So with angle stability, we have small signal stability and transient stability that are short term. And then with frequency stability, we've got short term and long term. And then with the short term is the one that we normally address in terms of the integration of renewable energy when we start looking at things like inertia, you know. But if we start looking at long-term effects like system flexibility, where we check generation balancing, then that becomes more or less long-term stability of the frequency, which is also another phenomena, you know, of that is brought about by renewables, you know, problems of flexibility. And then on the voltage stability, obviously we have a large disturbance voltage stability, as well as most disturbance voltage stability. Yeah, so that's our classical definition. Can you please confirm if you still hear me?
Yes, we
can still
can.
hear you.
Oh, beautiful, beautiful. So in terms of the revised classification, this is what we are looking at. Obviously, the revision came in because now we are transitioning as power systems around the world. There is now a large integration of renewable generation that are largely inverter based. So now, obviously, there had to be other type of stabilities that needs to be considered, especially in as far as inverters are concerned. You know, so the new definitions obviously now has like 5 classifications. So now we have resonance stability, which are electrical and torsional. So resonance stability will be things like torsional stability, that is subsynchronous resonance, a type of issues. Then we have now converter-driven stability. Maybe perhaps I go to converter-driven stability. I must state that resonance stability has always been there, but also, although it was mainly primarily included in frequency stability. So I think now they kind of like separated it. So now the other new baby on board is essentially converter-driven stability, and that you have a fast interaction and small slow interactions. Then we still have our classical rotor angle stability, as well as voltage stability and frequency stability. So in terms of the time frames, we know that we are dealing with different time frames, and I think it's very, very important to understand that when we start dealing with power system stability or any engineering problem for that matter, we normally would, as engineers, want to employ the theory of superposition, where we want to isolate the problem to say this problem, what is the cause, you know, cause and what is the root cause of this, you know, the cause and effect type of thinking. So we isolate the problem to that particular cause and deal with it in that manner. So that's the theory of superposition. We don't deal with the problem in its entirety, because if you look at power system stability, it's got so many elements in it. They're all intertwined. There is not like a one element X outside outside others. No ways. Yeah, if you have a frequency stability, you will have a voltage stability. You will have other things as effects coming off from that original maybe voltage stability. But so then we want to study the cause. So that's why we separate it like that, but not that they happen. The stability, when it happens, it happens independent of other stability issues. No. Yeah, other things may come in due to a primary cause. So we rather study the primary cause so we can solve it. I think that we are very clear. But in terms of the time frames, obviously, if we move from the prime mover, where the prime mover in terms of thermal power generation, the thermodynamic phenomena is a bit more slower type of phenomena. So it's in that range of 10 seconds to multiple seconds, 10 to the 5th seconds. Yeah, so that is the phenomena of thermodynamic, obviously, which influences a lot on our stability in terms of boiler constants, you know, water time constants, all those things. Yeah, then will be in the in the thermodynamic phenomena for things like thermal stations. So now you will move from there, then you go into the electromechanical phenomena, which now becomes the phenomena where now you're having electrical energy being now produced from obviously the prime mover and those interactions between your electrical torque as well as mechanical torque. So once we start having that, then those time frames are a bit smaller. We are talking about 10 to -1 to about 10 to 1 second. So there we are talking about milliseconds type of phenomena. And then if we leave that electromechanical phenomena. The electromechanical phenomena is normally the type of studies that we do a lot traditionally, that we used to do, that are called RMS studies, to study that phenomena, electromechanical, which basically would study like average values, you know, of your currents and voltages. So if you go further, then you go into the electromagnetic phenomena. So electromagnetic phenomena is normally what is classically known as the EMT type of studies, electromagnetic phenomena. And then this one now is where you are studying actually instantaneous values. So you study your normal 3 phases instead of the phasors that we or average values that we study under electromechanical. And then obviously further down, then we have wave propagation phenomena, which are things like your surges, basically, lightning surges, the switching surges, the inverter-based controls. Yeah, will fall under that, as well as resonance phenomena. And that's about it there. So now that we have explained the concepts at a high level in terms of stability in general, then we can go first into the impacts of distributed renewable energy on transient stability. Yeah, so this is a bit of not so much discussed phenomena, as to, because all the time we have always been discussing inertia issues when you talk about stability, which obviously is a big problem, you know, as we transition, as we integrate inverter-based generation. But we have done some studies in the past to see the impact on transient stability. And this impact was largely on distributed generation. So it's very important to understand that it's a distributed generation because it can change depending on the type of modeling that you're doing. So if we study transit stability, then we are reminded of the infamous swing equation, which basically states that your accelerating torque will equal your mechanical torque together with your electrical torque, across your system. So meaning that because there's a proportionality relationship between your torque and power, then that can still be applied to torque and power. But I think of importance is to note that in equilibrium state, so under steady state conditions type of thing, when you're operating the power system and everything is fine, in steady state, it's equilibrium. There's no accelerating torque on your rotors, on your machines. So you see that this relationship will equal to 0. Your Tm minus Te will purely be 0, and then you're home and dry and running the system nicely up until something happens like a disturbance. When a disturbance happens, that's when now the relationship changes. Then either your mechanical torque is greater than your electrical torque, or vice versa. And then now you have either an acceleration, either negative or positive, and then that's now where dynamics starts. So that's the basic of dynamics. They start once there is a disturbance. So it's almost like your normal control theory, where you have a disturbance, and then the ability of the system to basically ride through that disturbance is what defines your robust control measures, whether the system is robust enough to can ride through that particular fault. So that's when you start analyzing when there's a disturbance. So I think it's very important to understand that. Equilibrium, 0, nothing, everything is fine. And then, so if we go further in terms of transient stability background, I'm just touching on the few background that you know. We remember the power transfer equation that basically tells you that the power transferred across a corridor will be equal to the sending end voltage times the receiving end voltage over the impedance of the corridor, and then multiplied by the sine of the power angle, or what you call the torque angle sometimes if you're talking from a generator point of view. But that's the normal power transfer equation that we all know. And so in this particular case, if you look at the diagram there on the top, we have 2 generators. So the local generator is assumed to be an RE generation, and then the remote generator on the far end, you can see it's far across transmission lines. So that's our normal conventional generation. As we know that even in our traditional system, like the South African system, our conventional generation is far from our sources. So like, for instance, the Mpumalanga generation pool is a bit far from our book centers here in Gauteng, which will be large here. You still have load centers in Mpumalanga and Limpopo, but the bulk of it is in Gauteng and obviously in Western Cape as well, going towards the Cape. So then you see that we have that phenomena where you have generators a bit far from load centers. But when we integrate renewables, because they're modular, scalable, smaller, then they tend to be distributed and very close to the load centers. So we know as transmission engineers or power system engineers, we know that the moment you put generators close to the loads, then you are defeating a problem of losses on your lines. That is normally a big problem on the transmission system in terms of transmitting that power and calculating your maximum transfer limits across corridor. So normally when you start distributing it like that, then it will behave. You will find that your losses will kind of like reduce, when your generation is close to your center. So that's what we are trying to demonstrate here. Generation that is close to loads just to see what the impact would be, distributed generation. So if you look at your classical then power transfer curve there, then you see that the top part, the yellowish, or what is this color? It's orange color, and that would be your local generation. That would be representation of the power transfer for your local generation, where you see that now you are able to transfer more because the impedance is less from the local generator there. It's just the transformers to your load, and then so that's why then the power transfer is higher. The amount of power you can transfer across that transmission is higher, across that impedance is higher as a result. And if you look at the remote generation, then obviously you can transfer less because you're far, because of the impedance now comes into play, and you cannot transmit as much or transfer as much as you want to the load, because now you are on the far end going towards the load. You go via the transmission network and then transformers as well to get your load. So now you are now becoming constrained. So if we start looking at in terms of indicators of stability, what we call positive synchronizing torque, you'll see that your positive synchronizing torque is better with the local generator than the far off generator, because now we can see even the operating angle with a far off generator, which is the blue part, your operating angle now is bigger. For you to transfer the same amount of power, you have to operate at a higher angle. And if you are closer, you can reduce your operating angle on the rotor, the rotor of the machine, So that is the rotor angle. So already that tells you that obviously for stability purposes, what you want to do, you always want to keep your torque angles a bit lower, your rotor angles a bit lower. So that's normally what you want. You don't want to open it up. The moment you open up a lot, that's where now if your generator is operating at a higher torque angles, then it's a problem of stability again, that you are exposing yourself. Should something happen, that generator may run out of step. So you always want to be, I think the rule of thumb is to be around 30 degrees or so. So that is just a demonstration to show you what is happening there, that your positive synchronizing torque is improving because obviously you're getting closer to the slope, delta T over delta tau is getting closer to 1. So that's when your stability margins improve. But if it's now getting closer to 0, then that's where your positive synchronizing torque will diminish, basically, and then you are exposed for stability. All right, so that's what's happening there, that what we should keep in mind. We used some time back, probably 5 years back, when we were doing this test. I think it was at CSIR while I was still there. We used the IEEE 39 bus system to test this phenomenon. And then the results were as follows. This was just the base case of the studies. Then you can see these are the rotor angles of multiple generators. The fault was located at bus 16. It's just a random bus there on the previous diagram. And fault duration was 100 milliseconds. Fault cleared by tripping a line. Yeah, so that is just the base for that. So what we are interested in seeing is how this changes now as we integrate more renewable energy. So this is now, base case is 0% renewable energy penetration. So the different cases were studied, that is 20%, 40%, 60%, and up to 80% renewable energy penetration in that particular system. That is the New England system IEEE test case. And then it was found that at 80%, if you can see the correlation, the point is to see the correlation, the attenuation of this, of the the oscillations, or rather, I don't know if you call it the oscillation or the response, you know, the rotor angle response. We compare one graph to that. So you can see here clearly that at 20%, if we look at the bigger swing, it's just below 40 degrees there. And then if we increase to 40% renewables, then that swing that is positive there, the first one that we are seeing there, on the positive side, not on the negative side. On the positive side, then you can see that it's now below 20, half of that. If you zoom there, you see now it's below 20. So that's it's attenuating. So if it's no longer like a large swing, you start with for transient stability, it shows that your stability margins are improving. So the higher the swing, it shows you that your stability is not good. So if you have a disturbance and the rotor swings, so that it is normally made from the first swing, that is the transient stability. So if the swing is too high, then it already tells you that you're having problems of stability. It might be that now as time goes, if you get a nice fault, you may go out of step and you may not be able to recover that swing. So if the first swing is attenuating, it's a good sign that you are decreasing your stability margins, which is what we're seeing here. So you move from 40, go to 60, see that they become smaller and smaller. Now they're even way lower or lower than that 20 that we saw at 40, and 80 even lower at 80. So what it shows that in fact at 80 you see that it hardly gets to around this is 15, around 10, doesn't even get there. Yeah, so this attenuation of the first swing is showing you an increasing stability. So this is with the distributed renewable energy, you are seeing positive effects on the transient stability. Why? Because the distributed renewable energy are feeding directly into your load centers. You know, they don't have to transmit power over long distances, so that reduces your system losses. By so doing, that means that you're remaining, and it's very important to understand why we are doing transient stability, because someone will ask, what is the measure of this rotor angles? Because inverter-based stability, because largely your renewable energy will be inverter-based. So where are you getting the rotor angles from? The rotor angles are for the remaining generators, the synchronous generators that are there. Well, because what happens is that when you are having a generation close to the loads centers, then those generators at the far end that are your normal synchronous generators that now pull back. They don't have to provide power the way they used to provide it before. So that means now their governors pull back. Then when their governors pull back, that means now their operating angles pull back. So governing means that even the operating angles pull back. When the operating angles pull back in terms of that torque angle, then there is an improvement of stability. So that means they are not loaded as much as they would. You know, a synchronous machine, if it's loaded at full load compared to when it's loaded at half station or even lower, generally you might exhibit like a better stability. You know, so that's what is happening here, that your synchronous machines are pulling back because of the feed coming from your loads, and as a result you have improved stability. You know, so sometimes we need to talk about these things because they are there. It's one influence that's positive. It might not be looking at things in their full entirety, because there are other elements where you may find that now you might have problems with synchronizing torque, you know, but under certain circumstances, then I think I'll get to that. But that's normally, that's what will happen with distributed generation. And it doesn't have to be a renewable generation. Any generation that is distributed will add this type of phenomena to your remaining generators that were stressed. Now they will be relieved a bit. They will no longer need to export that much. So that now relieves them and then improves your stability margins in as far as transient stability is concerned. And in as far as we are looking within this bound, because once you throw another spanner, things could change a bit. So further analysis then will show you that now if you look at critical fault clearing time as well on your machines that are remaining, then you start seeing that your critical fault clearing time improves. Of the base case gives 115 milliseconds. At 20%, you see 173. At 40%, 257. 60%, 384, and then 80%, 367 milliseconds. So that tells you if your critical fault clearing time is increasing like this, it's a good indication that your stability margins are improving. Why? Because that means you can tolerate faults that are longer, you know. So that's another thing to remember, that the more you're tolerable of longer duration faults, faults that are lasting longer, then your stability is improved. So we tend to, when we do this index of a critical fault clearing time, if that index or if this time gets close to our normal standard breaker clearing time, you know, normal or protection clearing time, normally the transmission system would be around 100 milliseconds or so for, I think, for the ESCOM system. Yeah, many other systems would still conform to that, depending on the type of breakers that they use. You know, if they're using like the old 3-cycle breakers, they would have like 60 milliseconds to kind of like operate. You know, if you look at your cycle in a 50 hertz system, so your three pole breaker, 3-cycle breaker will be 60 seconds, and then I think then you put like 20 milliseconds of a flight time for your signals, and then maybe 20 milliseconds as a FET, as your FET. So that gives you a total of 100 milliseconds. You know, and so if you are now running away from that, you say, if a fault happens, I can tolerate up to 460. That means you are super good in terms of your stability margins. So that's what this measure says. But if it goes beyond your 100 milliseconds and it says 80 milliseconds, for instance, or 90 milliseconds, that means you are now seeing a lot of problems, because that means even your breakers now may not be able to save you when that particular disturbance happens. You know, they will not be quick enough, and that means you will have lost your generators or your system. So that's normally how the planning is done. So in this particular instance, for distributed generation, we can see that there is an effect improvement on stability in as far as transient stability is concerned. Okay, we further looked at other situations which are practical, which can happen on the grid, where you find that already your corridor of a transfer is constrained. You know, your distribution corridor is already constrained. So when you put generation in a corridor that is already constrained, maybe a line that is already overloaded, and even if you're putting that generator close to the load, but the line is already overloaded and it's got some operational problems, then it's a problem. Then you'll find that now you'll start experiencing some instability in as far as transient stability is concerned. You know, so sometimes you may find that things are not so nice. You may find that you do have corridors that are already at distribution level, where you are integrating this renewable generation, where you are already constrained. And then once you're already constrained, then you are likely to have transient stability problems instead of improving them. You know, with the remaining generators, they tend to become unstable. Your remaining synchronous machines, you don't relieve them in that particular case, because now you're adding a problem on basically by adding the generation, you're no longer solving the problem. So that's why I said you need to look at multiple things in this regard. It's not like it's a one-size-fits-all transit stability. I mean, renewable generation, distributed renewable generation solves transit stability problems. No, it's not one-size-fits-all. It's just that particular issue that we looked at where your distribution corridors were not constrained. But the moment you start constraining some of them, then you start having problems. But there is something positive that I think we needed to demonstrate in terms of the distributed generation, which largely your renewable would be. So in terms of the remarks, the study shows that distributed renewable generation affects the transit stability positively by increasing transit stability margins of conventional synchronous generators in a power system. So that's the effect. Then the distributed RE in close proximity to load centers plays a big role in realizing and improving transit stability margins in the power system. I think we have touched on that. The fact that inertia of the power system is eroded by integration of static RE generation does not necessarily mean that transit stability will also be affected negatively, as transit stability by its nature is more local as opposed to global. Sorry. So constrained corridors, which is what you've seen. So integration of RE generation on already constrained corridors will result in transit stability concerns. However, this is viewed as poor planning, as the corridor would have to be strengthened first prior to integration. So obviously that's a given. Yeah, but it's not always the case. And then again, if you look at the logistics surrounding that in terms of money and stuff, and obviously people competing for these networks. So if you are putting them on already constrained corridors, and then you don't see that effect at all. If anything, you're then going to see problems as far as the other generators of the synchronous machines are concerned. We're going to make the system more unstable. So I'll pass that in terms of the impacts on transit stability. Now we go on to the impacts on frequency stability. So here, what do we deal with? And mind you, remember that the impacts on transit stability when they happen, but I think I've already emphasized this, that it doesn't mean that they happen in isolation. Transit stability would mean a series of other things that are going wrong afterwards, not itself in isolation. It will happen as the cause for the problem, but then there are other effects that come in terms of affecting other stabilities. So when we look at frequency stability, here we are just looking at generation load balancing. And that's what frequency is defined as. You know, when your system is balanced, like in our South African system, which is operated at 50 Hertz, then you would have if the load and generation are equal, then you are home and dry at 50 Hertz. But if you have one side becoming bigger than the other, then obviously frequency will decrease or increase depending which side. If, for instance, generation increases, then if generation increases, that means now your frequency becomes higher. Or if your load increases, then that means your frequency becomes low. So this is just showing the normal control that is employed in terms of generator control of a turbine or speed control. So this is the normal control and philosophy that is employed for such. And then this shows what is termed power system inertia, where basically it's just the rotational energy of all rotating machinery in the power system aggregated together to give what is called the H constant of the system. That is now the stored rotational energy of the system divided by the MVA base of the system will give you your inertia constant of the system, and then your stored rotational energy, which is half J omega squared. where J is the moment of inertia of the rotating mass, and omega is the speed in RPM of the rotating mass, and system inertia then will be a summation of that, of the whole system, not necessarily an individual machine. So that is the rotational energy, and I think that we just need to understand that inertia from physics is resistant to change in motion. So if something is stationary, you want to move it, you always will experience a force that acts against that, in physics terms. Equilibrium, so you move any mass from a state of equilibrium, then you always get like Newton's third law of motion acting against you. So that's exactly what's happening here. System is in equilibrium, rotating at 50 hertz. So that's almost like equilibrium in as far as physics is concerned. It means zero. Because there is no difference, like we saw in the swing equation. So once you're there, if you start wanting to change that motion, that synchronous speed through a disturbance, maybe, then you will find that you will get some resistance coming off from the mass. The inertia of the mass will resist your action. So that's what's happening here. So this phenomena has been protecting us. We have been taking it for granted because it has been protecting the power system against the disturbances. It sort of like was damping the disturbances that were happening on the power system because of the perpetual motion of rotating machinery. So if there's a disturbance, that disturbance impact was largely dampened by the fact that you're already rotating. So that gives you a bit of resistance of or protection. I don't know how to call it, inherent energy that is resistive, to change. So that has been good to the system. But now that we are displacing synchronous machines with renewable generation, then we lose that inherent resistance to disturbances. Then we become more exposed to disturbances. When there's a disturbance, now the system dynamics just shoot through the roof, because now you don't have that resistance in terms of combating that particular disturbance. So I think some salient points to remember in terms of that: initial energy in the power system helps to arrange frequency deviations. So it minimizes them, not that it totally arrest them holistically. That means that then our traditional systems wouldn't be having problems. No, they were still having problems, but the problems are not as extreme as they would be in as far as frequency is concerned when we start integrating inverter-based generation, because now they don't have rotating parts. So a heavily loaded system is stiffer to frequency excursions than a lightly loaded system because of the larger amount of rotating machinery. Low frequency control and initial energy in the system help in damping smaller frequency excursions even before primary governing can activate. The displacement of synchronous generation with static, that is non-rotating generation, leads to high erosion of natural initial energy. Hence, the system becomes more malleable to frequency excursions. The rate of change of frequency increases as a result. System inertia reduces. This could result in relays failing to timelessly detect frequency excursions, and possible loss of frequency control could lead to system blackouts. And a weakly interconnected system is more prone to initial degradation, simply because it will not get enough support during frequency events. Yeah, so this phenomena, I think the last point is very important because it happens a lot in weak grids. Islanded grids that they're weak, meaning that they don't have support from their neighbor. So if there's no support from your neighbor in terms of strong interconnections, then the phenomenon of inertia is even much worse, because that means when you have an event, if you don't have protection in terms of that particular extreme events, then you are almost dead. But if you're looking at meshed systems, I always make an example that your normal Central Europe systems are very meshed, so that's why they don't have to study this phenomena that much, because now they always get support from each other very quickly. It's only the guys in the outskirts of Europe that will start looking at that, like the likes of your Ireland, because they are out now. They don't have that much support like that is enjoyed by the likes of Germany, France, Italy, for them, they even though obviously engineers will still know about this phenomenon, but it's not as it's not a much problem that it's not a big problem like Ireland will face. Ireland will face bigger problems. I think even the Nordic system as well, I think they realized a long time ago that also because they are slightly out and from the main Europe, they're on their own then, so then they also have to worry about this, and they've done a lot of work on it. Australia, on the other hand, it's already an island. They do a lot of work on this. Texas in USA, obviously being a bit isolated from the main US system as well, they also are big on this. South Africa, same thing, has to be big on this because in Africa, basically they're an island. So then they become, it becomes a problem. So if we look at what CRIC code states in terms of primary frequency response, the CRIC code or South Africa says that the requirement on the system operator is to keep the frequency above 49.5 hertz following all credible single contingency losses. The largest loss being the loss of a cubic unit that is 920. I think now it's 950. I think my ESCOM colleagues will correct me. I think it's 950 now. Yeah, but that is still the single largest contingency that the system operator needs to operate to. So that means the system operator needs to cater or always have reserves that will be able to help the system should they lose a cubic unit on full load, because that is the largest contingency, that the frequency may dip too far. So they need to have reserves, not necessarily exactly 920. You have to do a study to determine how much that they need to carry to combat or to prevent, to arrest the frequency should that cubic unit a trip. So that, and then that should always be arrested at 49.5. So if it's arrested below that, obviously that becomes now a flag to NESA, who is the owner of the document, and they will now start asking system operator what the problem is. So I don't know what the arrangements there are in terms of penalties, how long it takes before NESA will say they institute penalties. But normally that's how a system operates, requirements on the system operator from NESA. So so if you look at that phenomena, and now we are looking at increased penetrations of renewable energy in terms of the nadir, that is the turning point. Remember that the reliability in terms of the CRIC code, we need to turn at 49.5. But as you increase renewables and you're keeping the same amount of reserves, then you start seeing that your nadir falls now. So that means now you need to recalculate as the system is changing how much reserves you're supposed to carry, so that you are still observing the CRIC code. Otherwise, then you start violating the CRIC code, And I think we had done several studies that shows that I think the last one was around 60% penetration in the South African system. A similar model that we network for the South African system showed that you at around 60% penetration, not 60% penetration in as in like installed capacity, no, 60% of penetration is instantaneous penetration. That is now, sometimes you may find that even your 20% can easily become 60% during certain loading conditions, because now we are not talking about installed capacity. So that's why it's very important that I think ESCOM as well is doing a lot of the studies, because even with the current levels of penetration, it can be that especially around light loading, around now as we approach in summer, the system gets relieved a bit in terms of demand. That's where now you may find that now renewables penetration, could be higher in those type of situations where the load is low. Already if you have like 10 gigs of renewable and you're around December, Christmas time, the load is like 19 gigs, which it can get to, and you have 8 gigs of renewables, you almost like, over, yeah, you're almost very close to that value of 60%, and you could start seeing problems. So, but I'm not saying or indicating that that is the situation with the Eskom system. This was just a test case. Eskom obviously does its own studies where obviously they will determine where these particular limits are. Yeah. So, but we had done some test cases. I have done some studies as well for Eskom. I should confess with the CSIR. I'm still currently leading the CSIR team there, even though I'm running my own firm. But I still need to support CSIR in terms of supporting the engineers there. And from time to time, we work with Eskom, and we've done several of these studies, a lot of them. But obviously, it's not for public consumption. I'm not at liberty to share some of the results that we got. I think Eskom will do that in their own time. So if we look at the ancillary services suite, basically it's the ancillary services in this aspect is more about reserves management on the system, as I have said, that you have to carry a certain number of reserves. So that means you need to do a series of studies to calculate this reserve, especially as it relates to frequency stability or primary frequency response. So there are various things that you can do, but obviously over and above primary frequency response, you have other slower dynamics that I talked about that are in the region of what is called regulation of the frequency, which is secondary frequency control by a central system called automatic generation control, AGC. So you need to carry reserves there, and then post that, then you can still carry reserves as well for tertiary frequency control. So now this is when now you're dispatching units like it's no longer even automatic. Sometimes it could be manual, where you're calling in units as you. So this just shows that particular suit. Sorry, I think this is a repetition of what we've already discussed. And this as well. Sorry about that. Am I going back? Or sorry, looks like I'm going back. Sorry, I was going back. Yeah, so this just gives ancillary service, I think, for the European market, the type of ancillary services that they procure. Now, fast frequency response, I think this was given by NTSOE. Fast frequency response services, frequency containment services, frequency restoration services, replacement reserves, and so on and so forth. And so if now we go and now go into this mitigations of the problems that we have seen in as far as inertial degradation is concerned, we can deploy batteries to help with the falling nadirs. We saw that the system was falling as we integrate more renewables. So we realized that obviously, as we do studies, you'll find that even the amount of reserves that we're carrying on our current governing units, because the reserves will come from your governor. Remember, the governor, when it sees a frequency deviation, it will move. So normally, the generation that will carry reserves, normally I think the requirement from the system operator will be that that generator should not operate at full load. So that means it will leave a particular margin that the system operator will have determined to say this particular unit should operate at not more than 90% of their full output, so that now that room they reserve it for this primary frequency response, that when there's an event, then that machine can move. Otherwise, if it's operating fully, then obviously it won't move. So it needs to operate below. So the aggregated governing response from all the machines is the one that will provide the reserve margin that is required to close the gap and to arrest the frequency at the required level. But through our studies, we've seen that governor, if we keep those amount of reserves on the governors themselves, even if we increase the level that we have now, as we put in more renewables. If we increase the amount of reserves to a level that is greater than what we have now, we have seen that it's not helping because of the fact that the rock-off levels are too high. The rock-off levels are too high, and the response from the governors are too slow because remember they've got mechanical time constants. So for them to react takes time, and we have seen that it doesn't help. There is a point where you find that you are getting diminishing returns. You get so much reserves with so little impact, so it's that phenomenon of diminishing returns, so I think through studies, everybody in the world has seen that that governor response is no longer really capable to deal with this phenomena. So where do we need to go? We need to go into other phenomena, solve this thing with exactly the same phenomena, that is the inverter controls, because they're faster. So if you look at things like the battery response, it uses your inverters. The responses are like excellent. Your time constants are too small, so you get faster response. So the way to combat it, there's even a term called now fast frequency response instead of a primary frequency response. So now you need to carry fast frequency response, which would be in the form of batteries. But it doesn't mean that every battery that is put on the system is put for this. Some batteries are for energy arbitrage, some batteries are for secondary frequency control. So it's all about planning your resources to say, when I'm putting this particular battery at this particular point, this one I'll be dedicating to primary frequency response, or maybe you can even apportion it and say 10% of it will be primary frequency response or fast frequency response action, and then maybe another 10% will be now on secondary frequency control, in terms of balancing the system, or maybe the other one could be the remaining 80%. I'm just making an example, could be now on energy arbitrage. So I think that's what we need to understand, that batteries have this type of response. As you can see that the frequency going down there, you can see the response that the battery has. It's almost like instantaneous. So this is one of the simulations that we're doing, and this is coming mainly from Malawi. So if you check the response now of the battery in terms of the response of the governor, you can see here on the left-hand side, this is the governor rise time. You can see because of those mechanical time constants, we get the rise time. It's very slow, and then look at the battery rise time. For those that remember control systems, you can see that the rise time is like very high, and that's exactly what you want. So that's why now batteries are becoming like a solution to our problems, But the other element is that batteries are expensive. So maybe that's another thing that we have to consider. The technology is still not very fully matured. So we may not be able to, even though we can see this type of responses, we may not be able to procure what we want. So that's those kind of situations that we are facing as as the power system people, not necessarily South Africa problem, but it's a worldwide problem for systems that are exposed, like the South African system. The other mitigations could be in the form of a demand response, which is an easy one. Demand response is like basically contracting some big industrial loads. It doesn't even have to be industrial, as long as it's bulk loads. And obviously, this is you contract them, and then the system operator contracts them, and then they will deploy them as and when they want, when the system sees fit in terms of converting this frequency runoffs. So that means if a particular event happened and these things now have been contracted and they've got proper control settings with relays next to them, so then they will be triggered automatically to they will be cut off the system. So obviously that is something that happens between the system operator and the customer. So this is now, I think, an opportunity for even entrepreneurs to enter this type of space in terms of becoming aggregators, because that's a big thing. Where it doesn't have to be only industrial. big mines with big loads to provide this service, it becomes very easy for Eskom. But I think people see an opportunity. I think the market is opening now. There's no way it needs to open, and Eskom will be opening this type of things. I'm not sure if they're already not out in the market, but they are going to be there. It's just a matter of time, because that's what's happening around the world in terms of providing this innovation and everybody participating, so that people, I think it will even help in terms of knowledge that everybody participates in solving the system problems. It's no longer Eskom problem alone, but it's a South African problem. Own it wholly, and you get entrepreneurs that could even go to residential and start aggregating people and providing this as a service to say, Eskom, I've got like 100 megawatts from residential. This is how the model is going to work in terms of compensation and those kind of things. Yeah, but that's business now. But at a technical level, that's what happens. That's what happens. It gives relief. You can see the red curve there, and the green one. The green one is the one without that demand response. So if we add some megawatts of demand response, then you can see that for the same contingency, then the system nadir now improves. The other one here, I think here I'm just showing the relationship between BERS and governing response in terms of the frequency response. So you can see, if you look at batteries, the green one is a battery that is responding, and it was in the Malawian system, it was about 25 megawatts of battery injection, and there was no governing at all, but it managed to arrest the frequency very high at above 49.5, around 49.8 or so. That's where it was arresting it. But now with governing, something like a maximum governing, which was around, I think the maximum governing here was around probably 40 megawatts, then the frequency went down to almost 48.5 for a big contingency in their grid, So the contingency remains the same. So you can see the power of the battery. You don't need so much. The maximum governing here was around 40 megawatts, but with only 25 megawatts, then you get so much improvement. 25 megawatts of battery, you get so much improvement. So battery response is very superior. It's like even demand response. I think there is a situation where we compare demand response and battery response. I think battery kind of like comes slightly superior than demand response, but demand response is still phenomenal as well. So the other issue that needs to be calculated is what is called a critical rock-off or critical inertia levels. That obviously is the responsibility of the system operator to calculate those particular limits. So that now they know what is the critical limit here in South Africa and what they should do to combat it. So there are some studies that obviously were done to kind of like estimate those critical limits. Obviously they all have to be within their reliability limits. So we're testing multiple mitigations here in terms of getting those limits, critical rock-off limits or critical inertia limits. So as you can see now, when we zoom in, you'll see that the takeaway point here is that the system can tolerate higher rock-off levels. That means low inertia when fast frequency response services are deployed. So that means with the faster batteries, then you can tolerate to have low inertia. As long as you know that you have fast response mechanisms in place, then that means what that means is that you have now room to integrate more renewables. You just have to understand and see that you have the resources to deploy to combat, but you need to establish those limits. How far can I go? Because it's not like open-ended. You have to say, how far can I go? So that's those critical levels to say, maybe if I get to 60% penetration, I will need a gig BESS. I'm making an example. I'm not at liberty to share. We've done some studies, but I'm not at liberty to share, unfortunately. they are still the property of Eskom. Yeah, so it's that kind of thing, but those type of studies needs to be done, and we have done, like I've said, but I think they were submitted to Eskom. Eskom still needs to make a determination, and even maybe they are doing further studies, because it was not just us when I was leading the CSI engineers that were doing this type of studies. I think there are other groups, interest groups that have been assisting, and Eskom itself doing studies. So obviously it's them putting everything in one basket and having doing the sensitivities that are needed. They will know their network better to know where to adjust and to improve, and then communicate this if at all it needs communication. But I think it might need maybe to put in things like IRP. I think it's very important to put this type of limits there once they have been confirmed and sanctioned by Eskom. Future system studies. So static and dynamic studies of future operations are a key aspect of planning decisions and essential to future system needs. And understanding of these needs will underpin the definition of our future services, codes, and policies. However, such studies are non-trivial to attempt, and they need to include detailed, accurate dynamic models, which is always sometimes a big problem to source, especially even from your PVs, because the system operators sometimes they may need to have this type of models, and you find that it's always challenges because of patent issues with particular OEMs. Reasonable future scenarios, what dispatch, unit commitment and demand levels will exist, what policies and practices should appear in study assumptions, comprehensive understanding and appreciation of study limitations. What can my study tell me and what can it not tell me? You know, in terms of the key takeaways, power system stability is a concern for many utilities. Technologies exist to supplement or to improve this. That is, studies are essential to determine critical stability thresholds in future and guard against security issues. Battery energy storage systems and other mitigating measures can be deployed to combat system stability issues for power systems, more especially related to frequency stability issues. And as penetration levels of inverter-based generation continue to increase, power system stability margins degrade. Thus, the system operator, more especially in Southern African power pool, with the help of relevant stakeholders, should proactively meet these challenges using mitigating measures that we have mentioned here. And of primary importance is that the Department of Energy should institute power system studies for long-term planning and short-term operations horizons, so involving all relevant stakeholders to inform future IRP energy mixes post-2030. And system operators should develop an increased situational awareness of system inertia, ensuring primary frequency response capability from all generating sources, including inverter-based generation, and introducing the use of various forms of FFRs and necessaries, such as BESS. Yeah, so I think that brings us to the end of our presentation, ladies and gentlemen, and now I can hand over back to my host. Thank you.
Okay, now thanks a lot, Perry, for such an insightful presentation. Yeah, no, we are learning. Just to like to open to all the delegates attending this webinar, please type your questions in the chat box, and then we will be posing them to our presenter. So I have a few questions posted already. Okay, no, it seems like it was okay. Mpoyeng asked the question, would it be possible? Okay, my network is okay. No. He was asking for a recording. It will be uploaded on the YouTube channel. And then, has Eskom already done such study on IPG penetration already, or still in process, respecting confidentiality? This question is asked by Craig Mokel.
Okay, I think I have said many a times that we have undertaken studies with ESCOM, and ESCOM has undertaken studies even with not us. When I mean, it was myself leading the CSIR team. So we have done a lot of studies for this work with ESCOM in collaboration with ESCOM. It was ESCOM studies that, and we were doing them with them. I understand there are other initiatives and studies that are done with inside ESCOM, either by ESCOM and through other consultants and their partners in other, yeah. So they have been done, I can say that, but I don't know to what extent. Obviously, ESCOM will need to get comfortable in terms of the results and in terms of giving a clear direction in terms of where these limits are. They still need to do their own assessments, because my doing a study being outside ESCOM, I may not be able to capture all the phenomena and the understanding that they would have on the grid. So they still need to obviously review and see where improvements can be made, because they know the power system more than anybody else. Yeah. So I think there's a lot of these studies have been done. I can confirm.
Oh, okay. Thanks. Another question is coming from Naniki Zuza. It says, on a case showing improved transient stability with distributed generation as high as 80% due to renewable energy generation being closer to the load, how does this apply in long transmission lines transmitting power to load centers far away?
Yeah, I think that's exactly what we wanted to demonstrate there, that long transmission lines, because they are far, if you have a generating source that's far from your load, then you incur losses. And as a result, you start affecting if it's a synchronous machine on the far end, it starts getting strained in terms of power transfer. So your operating angle would increase for you to push that power down that transmission corridor. But if now you are putting in a generator right close to the load and you don't have to rely on the long transmission line, then you find that what that does is that the remaining generator on the far end of the line, that is the synchronous machine, will now pull back, because you are supplying power to the load directly. So the load now does not have to rely on that long transmission line to import power from that generator, but it's got a local generator that injects almost instantly. So what that does is that it improves the stability margin, that is the transient stability margin of that far off generator. So that's what we are trying to demonstrate. But again, I think this one should be understood in the fact that it was a test case. It was not done on the ESCOM system. It was done on an IEEE 39 bus system as a test case. Yeah. Yes, sir.
I think you broke off there when you're saying it should be understood.
Oh yes, I was saying that it should be understood that it was not done on the ESCOM system, but it was done on a test IEEE test case, 39 bus system, simply to prove a point.
Okay.
Yes.
Okay, no, thanks. And then another question coming from Walter Moilwa. Will the introduction of EV charge stations as the industry evolve, will that have an impact on the grid frequency?
The introduction of what, EVs?
Yes, yes, EVs, electrical vehicles.
Yes, no, it depends how you look at it. Yeah, it just depends really on what the plan is, the strategy. So if the strategy is that you are using EVs as to provide ancillary services, because the EVs will have batteries. So if they are not used and they are fully charged at night and they are staying there connected to the grid, and you want to use them for fast frequency response or for system bar for regulation, then yes, they are as good as batteries, so then they can help, with the system. But it all depends on the strategy at the end of the day. But if EVs are there and you don't tap into that capability, then obviously you're not going to see, it's not like by the mere effect of them being in the system then solves the issues. No, it's all about strategy in terms of what you want to use them for and the kind of agreements that will be put in place. The landscape is changing. Everything, like now we are having demand becoming now even, participating. That type of demand is no longer demand as we know it. People now are going to start participating in this, but it's all about strategy and opening up the market to that effect.
Okay. No, thanks for that answer. The next question is coming from Blessing Siabonga Ndlovu. Okay. How does the positioning of the BESS on the grid affect its effectiveness in maintaining power system stability?
How does what? Can you repeat the question?
The question says, how does the positioning of the BESS on the grid?
Oh.
Yes.
Positioning.
Can you hear me, Mpedi?
Yes, I can hear
Sorry?
you.
Okay.
I can hear you.
It says, how does it? Okay. It says, how does the positioning of the BESS on the grid affect its effectiveness in maintaining power system stability? Question by Blessing Siabonga Ndlovu.
Oh, okay. The positioning, I think that's the key word, because BESS does improve, but the positioning is where now it's an operative word. Yes, it's all about position really. When you study these things, it's not at the system level. You have to do optimal placement type of studies to see an optimal position that where you put the BESS, it will have the most impact in terms of the mitigation that you're trying to come up with. So yes, you are very right. You have to do optimal placement. It's not just like I can put BESS anywhere and expect the same type of response. No, I have to optimally place that and see where do I get the best effect from this. So yeah, that's how it is.
Okay, thanks. Our next question is coming from Neo Mapapanyane.
Okay.
It's the question goes like this: for RPP models used in the analysis, did you use validated or generic models?
For RPP models,
yes.
I'm not sure for which one specifically, but it's a very cornered question because it will want me to disclose things that I don't want to be disclosed. Look, but in simple terms, in IEEE 39 bus system, obviously we used the generic models because it was a test case. But in the studies that we did for utilities like Malawi, I think I showed some studies for ESCOM, then obviously the IPPs there would be, the RPP models would be coming from those utilities themselves. When we did the Malawi studies, then they would provide the data. We'll ask them to go to the RPPs and give us the data, and then and prior to our doing the studies, you will find that they would have done validation of those models. So I think the same goes to ESCOM, where when we do studies with them, that is where we start. You cannot just use generic models per se. You need to get data from ESCOM. But if ESCOM's models are generic, then obviously there's not much that you can do, because it's them that will need to request a validated. Will need to validate those models themselves. It's not even the RPP validating. ESCOM validates the models, and then for them to use them. So for utility type of studies, my assumption is that they are validated. But for test cases where we are just demonstrating, it's a generic models.
Okay, thanks. The next question is from Zuko Ruba. It goes like this: are there any studies that look into how PES can help with rotor angle stability?
The studies that look into how to deal with rotor, there are many. Like I demonstrated, rotor angles at the transit stability. They've been studied for long. I mean, in power systems, the mitigating rotor angle stability has been widely studied, in the power system environment for ages. It's not a new thing at all. So there are a lot of studies and techniques that are used, but the techniques might not be applicable in this realm that we are going into, of faster dynamics, where now you may find we have problems. But there are various techniques that are used for transient stability, such as fast valving techniques, such as what do they call these things? It's fast valving techniques that you will be employed on the governors. Then you have like resistor banks, that are baiting resistors, those kind of things. But I mean, like, I didn't put them in simply because it's not, those techniques are sort of like waning down because now we are seeing new phenomena, but they're there.
Yes. Sorry, Pete. He was asking in terms of like PES. So the question was about PES in particular in terms of rotor angle stability. If there are studies, if it can help.
Oh, for rotor angle stability.
Yes.
It just depends in what manner. I don't see how, in what manner. Remember, rotor angle is for synchronous generators. So we need to be careful that this is when we are transitioning. So if you're going to be having a transient stability problem and now you want to solve it with PES, I don't think so. I'm not quite sure how that will look like. Yeah, maybe I'll need to apply my mind to it. I don't know how you want to do that. Okay, yeah, maybe it could still work in the sense where you have a base, and when you have a generator chip, for instance, and your generation, yeah, it could still have, if you are going to use it to, if you had a generator chip and the rotor angle went out of, was about to go out of step, and then you have an automatic base that can be deployed, obviously they need to sort of like come and balance that that system, if let me see. But it's more about this one, the rotor, the transient stability is not an energy one, so I might even mess it. It's more about the reactive power and the voltage support, not necessarily the power. So even that base, even if it comes, it will have to be not just about injection of the energy. It's more about control of the voltage, and reactive support, that the inverter-based generation may struggle to provide, So it's a touch and go, yeah. So I think a lot of things are still opening up. Yeah, things needs to be tested. So I think it's a good question, but needs further exploration.
Okay. Another question is by, we just have about 2 or 3 more questions, by Tabang Lebusa. What impact of renewable on protection schemes due to grid integration? Yeah, that's how it's written.
What?
So, I think is saying what is the impact of renewable energy on protection schemes due to grid integration. I'm thinking probably renewable energy on the integration onto the grid.
Yeah.
So
Yes, no. Very, very good question. Very, very good question. Relevant. Absolutely, there are other protection phenomena that comes to the fore. The pity is that I'm not a protection engineer, so obviously I wouldn't be able to unpack that nicely for you guys, for my colleagues here. But yes, there are a lot of challenges that are coming to the fore because of inverter-based generation, in particular, introduction in as far as protection is concerned. So things like what is called system strength, where you may find that now as you're introducing inverter-based generation, then your fault levels, get affected in terms of how you see those faults, because now they get reduced drastically to an extent, sometimes maybe where you may not be able to see them, and they obviously will reduce your system strength in terms of the rigidity of that, or the strength of the particular point where they are integrated, and so there's a lot of protection issues. Obviously, it's for protection engineers to unravel, but yeah, you should look at things like system strength and start studying that phenomena. It's relating to exactly that. Yeah.
Okay, thanks. Another one is by Janet Gillespie. I hope I pronounced it right. It says, does distributed battery power help with inertia? Do the batteries that people have installed for load shedding have any impact on frequency recovery?
Do batteries that people have installed in their homes have any impact on frequency recovery?
Yes.
Oh. I wonder in what manner. Yeah, you have to think of the situation. It's not like just installing batteries at our homes solves the problem. This is a system phenomena that we need to understand, that there needs to be plans in place to help the system. And even if customers are going to respond, they need to be part of the plan. It's not just done haphazardly. We are putting PVs and putting batteries and we are solving the problem. No. It's a matter of saying, system operator, how are they thinking about us having batteries in our home? Can they tap into that? Because obviously there's an opportunity right there, but only if system operator taps into it and opens up, and there's a strategy to sort of like now say, when there's an event, now we can aggregate the batteries that people have and then let them inject into the system. Then yes, they can help, but it's all about a concerted effort, especially coming off from the policymakers, not even just the system operator, the DOE, enforcing maybe the system operator to say, this is the direction we're taking in terms of the evolution of the power system, going forward. So batteries can certainly help, as you can see, but having them in our homes means nothing if there is no policy direction in as far as tapping into those resources are concerned.
Okay. There's two questions in the last 2 minutes we have. Given the increasingly unpredictable inverter-based distributed generators such as roof-mounted PV, how much control does the power system operators have on the grid inertia?
Can you repeat?
So, given increasingly unpredictable inverter-based distributed generators, such as roof-mounted PV, how much control does the power system operators have on the grid inertia?
Oh, I think it's exactly what I have just answered, that
Yeah.
they don't have any control, the system operator, up until there is an initiative to use them, to help them. If they are not using them to help them, then they remain, because remember, when there is load shedding, or if I want to cut off my system and I have my battery here, just switch off at the mains where Eskom municipality is coming in, and then I'm home and dry here, with my battery, so I've got full control and I'm autonomous, but if there is initiatives to sort of like that are looking at harnessing that that capability that we people now are having in terms of strategy, then they will be useful. But I think you also need to look at the phenomena in different ways in terms of if people now are becoming self-sufficient as well, in as far as energy needs are concerned, they become a relief on the system. So inherently they start affecting and helping the system, because now they become you know, like I'm saying, they are relieving the system. You know, they are no longer needing power from the system. So in a way, they reduce the strain, and that will help the system in the bigger scheme of things. So it's how you look at it. It's both strategy, and at the same time that there are some inherent benefits here and there as people become autonomous.
Okay. No, thanks a lot, Mpedi, for such an insightful presentation. We have run out of our time for this session. Yeah, there's about 2 questions that were not addressed, but I think then we can forward them to you, and we can maybe have them answered. Mings will guide how we'll have them answered. So thanks, colleagues, for attending this session. Enjoy the rest of your evening.
Thank you, sir. Thanks a lot. Goodbye.